Imagine a planet where it rains molten glass sideways at 7,000 kilometers per hour. A world where the ground beneath your feet is made of burning ice. A planet so dark it absorbs 99% of all light that touches it, blacker than coal. Blacker than any substance we've ever created on Earth. These worlds exist, they're real, and they're stranger than anything science fiction ever imagined. For most of human history, we knew of only one planetary system, ours. 8 planets orbiting a single star in orderly, predictable paths. We assumed the universe would be filled with solar systems just like ours. Familiar, comprehensible, safe. We were wrong. In 1992, astronomers detected the first planet orbiting another star. Since then, we've discovered over 5,000 exoplanets, and every single one has challenged our understanding of how planets form, how they behave, and what's possible in this universe. We've found planets that orbit to stars simultaneously. Planets with atmospheres made of vaporized rock. Planets drifting alone through interstellar space with no star at all. Planets where the entire surface is an ocean thousands of kilometers deep. Super-Earths, hot Jupiters, mini-Neptunes, and worlds that defy classification entirely. The universe isn't filled with copies of our solar system. It's filled with bizarre exceptions, strange outliers, and impossible worlds that exist anyway. Each discovery forces us to expand our definition of what a planet can be. Each new world reveals that nature's imagination far exceeds our own. Today, we journey through the most extreme, bizarre, and fascinating planets ever discovered. From the scorching hell worlds orbiting closer to their stars than Mercury orbits the Sun, to frozen super-Earths wandering the darkness between stars. From planets with skies of ruby and sapphire to worlds where metal snow falls upward. From ocean planets hiding beneath kilometers of ice to planets being actively destroyed by their own suns. The reality of exoplanets is stranger than any fiction, and it's just beginning. Prepare yourselves. We begin. The story of exoplanet discovery begins with failure. For decades, astronomers searched for planets around other stars and found nothing. The problem was simple. Planets don't emit light. They only reflect the light of their parent stars. And even a giant planet like Jupiter reflects so little light compared to the Sun that detecting it from another star system would be like spotting a firefly next to a searchlight from 1,000 kilometers away. By the 1980s, many astronomers had given up. Detecting exoplanets seemed impossible with existing technology, but a few researchers refused to quit. They knew planets had to be out there. The question wasn't if, but how to find them. The breakthrough came from thinking differently. Instead of trying to see the planets directly, astronomers realized they could detect planets by observing how they affect their parent stars. When a planet orbits a star, it doesn't actually orbit the star's center. Both the star and planet orbit their common center of mass. For a massive planet orbiting close to its star, this causes the star to wobble slightly, moving toward us and away from us as the planet circles. This wobble changes the star's light through the Doppler effect. As the star moves toward us, its light shifts slightly bluer. As it moves away, the light shifts redder. The shift is tiny, measured in meters per second, but it's detectable with precise enough instruments. In 1995, Swiss astronomers Michel Mayer and Didier Queloz pointed the observatory of Hut-Provence telescope. He had a sun-like star called 51 Pegasi, 50 light-years away. They measured its light carefully, looking for the telltale wobble of an orbiting planet. They found it. The star was wobbling with a period of 4.2 days. But when they calculated the mass and orbit of the planet causing this wobble, they discovered something that shouldn't exist. The planet orbiting 51 Pegasi was massive, at least half the mass of Jupiter, but it was orbiting its star every 4.2 days. That meant it was incredibly close to its star, only about 8 million kilometers away. 20 times closer than Earth is to the Sun, closer than Mercury. This was impossible according to everything astronomers knew about planetary formation. In our solar system, small rocky planets orbit close to the Sun and gas giants orbit far away. This pattern made sense. Close to a star, it's too hot for gases like hydrogen and helium to condense into planets. Gas giants can only form in the cold outer regions of a solar system, where ices and gases freeze out of the protoplanetary disk. Jupiter formed at 5 astronomical units from the Sun, Saturn at nearly 10. That's where gas giants belong. But 51 Pegasi b, this massive gas giant was orbiting less than 0.05 astronomical units from its star. At that distance, the temperature would be over 1,000 degrees Celsius. The planet's atmosphere should be boiling away. The planet shouldn't exist. Astronomers were skeptical. Many thought Mayer and Queloz had made a mistake, that they were seeing stellar oscillations or instrumental artifacts, not a planet. But within months, other teams confirmed the discovery. The planet was real. 51 Pegasi b was the first hot Jupiter, a class of planets that dominated the early years of exoplanet discovery. These gas giants somehow ended up in tight orbits around their stars, completing full orbits in just days. They represented something completely unexpected, a type of world that didn't exist in our solar system and that planetary formation theory said couldn't exist anywhere, but they did exist, and they were everywhere. Once astronomers knew what to look for, discoveries accelerated. By 2000, 34 exoplanets had been confirmed. By 2010, over 400. By 2020, over 4,000. Each new discovery revealed more diversity, more strangeness. Astronomers found planets orbiting binary star systems, planets with wildly elliptical orbits, planets being torn apart by tidal forces, planets in orbits that should be unstable but somehow persisted. They found planets much larger than Jupiter, massive enough to blur the line between planet and brown dwarf. They found planets smaller than Earth, rocky worlds orbiting red dwarf stars. They found planets with densities lower than styrofoam and planets denser than iron. The detection methods improved. In addition to the radial velocity method, which measures stellar wobbles, astronomers developed the transit method. When a planet passes in front of its star from our perspective, it blocks a tiny fraction of the star's light. The star dims slightly, then brightens again as the planet completes its transit. By measuring these dimming events, astronomers could detect planets and calculate their sizes. In 2009, NASA launched the Kepler Space Telescope specifically to hunt for exoplanets using the transit method. Kepler stared at 150,000 stars simultaneously, watching for the telltale dimming that indicates a planet crossing in front of its star. Kepler revolutionized exoplanet science. During its mission, it discovered over 2,700 confirmed exoplanets and identified thousands more candidates. It revealed that planets are common, that most stars have planets, and that the galaxy contains billions of worlds. But Kepler also revealed how bizarre those worlds could be. One of Kepler's most surprising discoveries was that the most common type of planet in the galaxy doesn't exist in our solar system. Super-Earths are planets larger than Earth but smaller than Neptune, with masses between 2 and 10 Earth masses. They're everywhere. Roughly half of all Sun-like stars have at least one super-Earth orbiting closer. Then Mercury orbits the Sun. They're the most common type of planet we've found. But our solar system doesn't have any. We have Earth, which is, well, Earth-sized, and we have Neptune, which is 17 Earth masses. Nothing in between. The most common type of planet in the galaxy is missing from our own solar system. This was our first hint that our solar system might not be typical, might not be the template for understanding planets throughout the universe. Super-Earths come in bewildering variety. Some are rocky, like scaled-up versions of Earth. Others are mini-Neptunes with thick hydrogen atmospheres. Some orbit so close to their stars that their surfaces are molten lava. Others orbit in the habitable zone where liquid water could exist. Kepler 4-5 to be discovered in 2015 orbits a Sun-like star at a distance similar to Earth's orbit. It receives about 10% more energy from its star than Earth receives from the Sun. If it has a rocky surface and an atmosphere, it could have liquid water. It could potentially be habitable, but it's 60% larger than Earth and possibly 5 times more massive. What would life look like on a world with 5 times Earth's gravity? What would the atmosphere be like? The weather? The geology? We don't know. We've never seen a planet like this up close. We can only speculate. But the discovery of super-Earths raised profound questions. Why doesn't our solar system have them? What happened during our solar system's formation that's different from most other systems? Are we the exception or the rule? The evidence forces us to confront an uncomfortable possibility. Our solar system might be unusual, possibly even rare. The planets we grew up learning about might not represent the typical architecture of planetary systems. We might live in a galactic outlier. In 2005, astronomers discovered HD 189733b, a hot Jupiter orbiting a star 63 light-years away in the constellation Vulpecula. At first, it seemed like dozens of other hot Jupiters, but when astronomers studied its atmosphere in detail using the Hubble Space Telescope and the Spitzer Space Telescope, they discovered something remarkable. The planet's atmosphere is blue, deep cobalt blue, almost exactly the color of Earth's sky. But the similarity ends there. On Earth, our sky is blue because nitrogen and oxygen molecules scatter blue light more than red light. On HD 189733b, the blue color comes from something entirely different: silicate particles in the upper hemisphere. Tiny grains of glass created when silicon oxide condenses at high temperatures. HD 189733b orbits its star every 2.2 days at a distance of only 4.6 million kilometers. The star-facing side of the planet reaches temperatures of over 1,200 degrees Celsius. At these temperatures, silicon oxide vaporizes on the day side, rises into the atmosphere, and is carried by fierce winds toward the night side. As the gas moves away from the intense heat, it cools, but it gets stranger. The planet is tidally locked, always showing the same face to its star, just as the moon always shows the same face to Earth. This creates an enormous temperature difference between the day side and night side. The day side is over 1,000 degrees. The night side is around 700 degrees. This temperature gradient drives winds of catastrophic violence. Observations suggest wind speeds of up to 7,000 kilometers per hour, more than 5 times the speed of sound on Earth. These winds carry the glass particles from the day side to the night side in violent storms. The glass particles don't just float gently through the atmosphere. They're driven by winds fast enough to shred anything in their path. It rains glass on HD 189733b sideways at supersonic speeds, and the wind doesn't just carry glass. Spectroscopic observations have detected magnesium, sodium, and other metals vaporized in the extreme heat. The atmosphere is a toxic mixture of vaporized rock and metal, glass shards, and hydrogen gas, all moving at speeds that would destroy any spacecraft instantly. This is a planet where the weather includes molten glass shards moving faster than bullets. It's a world that makes Venus look hospitable by comparison. JWST, to be discovered in 2008, orbits a sun-like star 870 light-years away. It's one of the hottest exoplanets ever discovered, with dayside temperatures reaching 2,800 degrees Celsius, hot enough to vaporize iron. But temperature isn't what makes WST to be remarkable. It's the fact that the planet is dying, and we're watching it happen. WST to be orbits incredibly close to its star, completing an orbit every 1.1 days. At this distance, the star's gravitational pull creates enormous tidal forces that stretch the planet into an egg shape. The planet's outer layers are literally being pulled away by tidal forces and stellar winds, forming a disk of gas around the star. Observations from the Hubble Space Telescope in 2010 revealed that the planet is losing mass at a rate of about 6 billion tons per second. That's roughly 189 trillion tons per year. At this rate, the planet will be completely destroyed in about 10 million years. A blink of an eye in cosmic terms. But the planet's death is creating something beautiful and terrible. As material from the planet spirals toward the star, it forms an accretion disk, similar to the disks around black holes. This disk is heated by friction and emits ultraviolet light. The dying planet is literally glowing as it's torn apart. Spectroscopic analysis has revealed that the material being stripped from the planet includes carbon compounds. In fact, WST appears to be carbon-rich, possibly with an atmosphere containing carbon monoxide and a surface possibly covered in graphite and diamonds. As this material is ripped away, diamonds are literally being scattered into space. The planet is so hot that molecules in its atmosphere break apart into individual atoms. Water, carbon dioxide, methane, all the familiar molecules decompose. The atmosphere is a plasma of hydrogen, helium, carbon, and oxygen atoms glowing with heat. WST represents planetary death in action. It's a reminder that planets aren't eternal. Given enough time and extreme enough conditions, even worlds as massive as Jupiter can be destroyed. JWST, discovered in 2006, orbits a star about 750 light-years away. It's a hot Jupiter, slightly larger than Jupiter, orbiting very close to its star. But this planet holds a distinction unlike any other. It's the darkest planet ever discovered. JWST reflects less than 1% of the light that hits it. It's blacker than coal, blacker than any paint, blacker than the darkest material ever created in laboratories on Earth. If you could see it against the darkness of space with the unaided eye, it would be almost invisible, a void in the stars. Why is it so dark? Astronomers aren't entirely certain, but they have theories. The planet orbits so close to its star that its temperature reaches 1,100 degrees Celsius. At these temperatures, atmospheric chemicals that would normally be reflective break down. Light-absorbing compounds like vaporized sodium, potassium, and titanium oxide form in the upper atmosphere. But there's another possibility that's even stranger. Some astronomers suggest that the planet's atmosphere might contain exotic materials that simply don't exist naturally on Earth. At extreme temperatures and pressures, familiar elements combine in unfamiliar ways, creating compounds with properties we've never observed. The darkness might come from materials we've never encountered, substances that can only exist in the extreme conditions of hot Jupiters. Yet despite being incredibly dark, JWST isn't completely black. Observations suggest it glows faintly red, like a burning ember. This isn't reflected light but thermal emission, the planet radiating its own heat into space. The temperature is so high that the planet itself glows, visible not by reflected starlight but by its own infrared radiation. Imagine standing on JWST. If you could survive the heat and pressure, you'd be on the darkest surface imaginable, absorbing almost all light, yet surrounded by a faint red glow as the planet radiates heat. The star overhead would be enormous, filling much of the sky, but the ground beneath your feet would be darker than the space between stars. JWST challenges our assumptions about how planets interact with light. We tend to think of planets as reflective bodies, shining by reflected starlight. But in extreme conditions, planets can become nearly perfect absorbers, black holes in miniature, swallowing light and radiating only heat. Kepler-16b. The Tatooine planet 51 minutes and 0 seconds to 55 minutes and 0 seconds in 2011, the Kepler Space Telescope discovered Kepler-16b, a planet orbiting to stars simultaneously. This was the first confirmed circumbinary planet, a world with two suns. Science fiction writers had imagined such worlds for decades. Star Wars featured Tatooine, Luke Skywalker's home world, with its iconic double sunset. But astronomers weren't sure if circumbinary planets could actually exist. The gravitational dynamics of binary star systems are complex. The two stars orbit each other, and any planet must orbit both while dealing with constantly changing gravitational forces. Planetary orbits should be unstable in such systems, with planets either crashing into one star or being ejected into interstellar space. But Kepler-16b exists anyway. It's a gas giant about the size of Saturn, orbiting to stars every 229 days. The two stars, both smaller than the Sun, orbit each other every 41 days. From the planet's surface, if you could stand on a gas giant, you'd see the suns circling each other in the sky, one orange, one red, casting double shadows and creating sunrises and sunsets unlike anything on Earth. The discovery of Kepler-16b opened a new frontier. Since then, astronomers have found dozens of confirmed circumbinary planets. They come in various sizes and orbits, from hot Jupiters completing orbits in weeks to worlds in wide orbits taking years. These discoveries revealed that planet formation is more robust than anyone expected. Even in the chaotic gravitational environment of a binary star system, planets can form and maintain stable orbits for billions of years. Nature finds a way, but Kepler-16b also raises questions about habitability. The planet itself is a gas giant, uninhabitable. But could a circumbinary system host habitable rocky planets? Could there be worlds with two suns where life might arise? The mathematics suggests it's possible. The gravity is complicated, but stable orbits exist in the habitable zones of many binary systems. Somewhere in the galaxy, there might be a world where alien astronomers watch two suns set, one after the other, painting their sky in colors we've never seen. But this represents just one piece of a much larger puzzle, hidden in the diversity of exoplanetary systems. Gliese 1214b, discovered in 2009, orbits a red dwarf star 48 light-years away. It's a super-Earth about 2.7 times Earth's diameter and roughly 7 times Earth's mass. At first, it seemed like another in the growing catalog of super-Earths, but when astronomers calculated its density, they realized something extraordinary. Gliese 1214b is to light. With its size and mass, its average density is only about 2 grams per cubic centimeter, much less than Earth's 5.5 grams per cubic centimeter. This low density suggests the planet is composed mostly of water. Not water, models suggest that Gliese 1214b might have, but at the pressures and temperatures involved, this wouldn't be normal water. The planet orbits close to its star, with surface temperatures around 200 degrees Celsius, under the enormous pressure of hundreds of kilometers of overlying water. The ocean would transition through exotic phases of ice that exist only at extreme pressures. On Earth, water freezes at 0 degrees Celsius at normal pressure, but at high pressures, water can remain solid at temperatures well above its normal freezing point. There are multiple types of ice, each stable at different combinations of pressure and temperature. Some of these ices, like Ice V and Ice X, are solid even at temperatures that would boil water at Earth's surface. Deep in Gliese 1214b's ocean, the pressure would be millions of atmospheres. At these pressures, water transforms into exotic crystalline structures, hot ice that's solid despite temperatures of several hundred degrees. Below that, there might be layers of superionic ice, a bizarre phase where oxygen atoms are locked in a crystal lattice, while hydrogen atoms flow freely through it like a liquid within a solid. At the very bottom, compressed against the rocky core, water might be compressed so much that it takes on properties more like a metal than a liquid. It would conduct electricity. It might be opaque. It would bear no resemblance to the water we know. Gliese 1214b represents an entire class of planets that don't exist in our solar system. Water worlds where H2O is the primary component, not just a surface feature. These planets might be common. Many super-Earths and mini-Neptunes discovered by Kepler have densities consistent with water-rich compositions. But could life exist on such worlds? Life as we know it requires liquid water, but it also requires solid surfaces or at least stable environmental niches. On a planet where the ocean is hundreds or thousands of kilometers deep, with no solid surface except at crushing pressures and extreme temperatures, could life emerge? Could it survive? We don't know. But water worlds expand the range of environments we must consider when thinking about where life might exist in the universe. The first confirmed exoplanets weren't discovered around a normal star. They were found orbiting a pulsar, the collapsed remnant of a massive star that exploded as a supernova in 1992. Polish astronomer Alexander Volshin discovered periodic variations in the radio pulses from Sir B1257 plus 12, a pulsar 2,000 light-years away. The variations indicated that at least 2 planets were orbiting the pulsar, their gravity causing tiny wobbles in the pulsar's rotation. This was shocking. Pulsars are neutron stars, the collapsed cores of stars that exploded in supernovae. When a massive star goes supernova, it releases more energy in a few seconds than the Sun will emit in its entire lifetime. Any planets orbiting the original star should be completely destroyed, vaporized in the explosion. Yet here were planets not just surviving but orbiting in stable, nearly circular orbits around the dead star's remnant. How could they be there? The leading explanation is that these aren't the original planets. They formed after the supernova from the debris disk created by the explosion. When the star exploded, it ejected its outer layers into space. Some of this material fell back and formed a disk around the newly formed pulsar. From this disk, new planets condensed. These are second-generation planets born from the ashes of stellar death. Later observations confirmed 3 planets in the system, all roughly Earth mass, orbiting between 0.19 and 0.46 astronomical units from the pulsar. They're subjected to intense radiation from the pulsar's magnetic field and rapid rotation. The surface of these worlds would be bathed in X-rays and gamma rays. Any atmospheres would be stripped away. The surfaces would be sterilized, lifeless, irradiated wastelands. But they exist. They're real worlds, orbiting a dead star in a system that shouldn't have planets. The discovery of pulsar planets revealed that planet formation can happen in the most extreme circumstances imaginable, even after a star dies violently, even in the harsh environment around a neutron star. Planets can form. Nature is more creative and resilient than we ever expected. Since Wolfson's discovery, a few more pulsar planets have been found, though they remain rare. Most planets probably don't survive their star's death, but some do, in one form or another, and new planets can be born from stellar ashes. This discovery also raised a haunting possibility. Billions of years from now, when our sun dies and becomes a white dwarf, could new planets form from the remnants? Could some distant future solar system arise from the same material that now makes up Earth, Venus, Mars, and Jupiter? 209,458b. The evaporating planet THD 09,458b, discovered in 1999, was the first exoplanet detected transiting across its star. This allowed astronomers to study its atmosphere by observing how starlight filters through it. During transits, what they found was unprecedented. The planet is losing its atmosphere rapidly. 209,458b is a hot Jupiter orbiting its star every 3.5 days. The intense stellar radiation heats the upper atmosphere to temperatures exceeding 10,000 degrees Celsius. At these temperatures, hydrogen atoms have enough energy to escape the planet's gravity. Observations from the Hubble Space Telescope in 2003 detected a huge cloud of hydrogen surrounding the planet, extending far beyond its normal atmosphere. The cloud is shaped like a comet tail, streaming away from the star due to stellar wind and radiation pressure. The planet is literally evaporating, losing millions of tons of atmosphere every second. Subsequent observations detected heavier elements like carbon and oxygen in the escaping atmosphere. These elements should be too heavy to escape easily, but they're being dragged along by the hydrogen flow. The entire upper atmosphere is being blown into space. At the current loss rate, 209,458b will lose a small fraction of its total mass over its lifetime. The planet itself won't evaporate completely, but smaller planets in similar orbits might not be so lucky. Astronomers have since discovered other evaporating planets. Kepler 150b, a Neptune-sized planet, is losing so much atmosphere that it might eventually be stripped down to a rocky core, transforming from a mini-Neptune to a super-Earth over hundreds of millions of years. This process, called photoevaporation, might explain one of the puzzles of exoplanet demographics. When Kepler surveyed thousands of exoplanets, it found a strange gap in the size distribution. There are plenty of planets about twice Earth's size and plenty about 4 times Earth's size, but few in between. This radius gap, around 1.5 to Earth radii, might be the result of photoevaporation. Planets that start out as mini-Neptunes with thick hydrogen atmospheres, orbiting close to their stars, might lose their atmospheres over time, shrinking down to rocky super-Earths. The gap represents the boundary between planets that retain their atmospheres and those that lose them. This means that many of the rocky super-Earths we observe today might have started as much larger planets with thick atmospheres. They've been sculpted by their stars, stripped of their outer layers, leaving only the rocky cores behind. The universe is dynamic. Planets don't just form and remain static. They evolve, they change, and in extreme environments, they can be completely transformed or even destroyed. KELT9b, discovered in 2017, holds the record as the hottest exoplanet ever found. It orbits a massive blue star 670 light-years away, completing an orbit every 1.5 days. The dayside temperature reaches 4,600 degrees Celsius, hotter than many stars. At these temperatures, molecules don't exist. Everything breaks apart into individual atoms. Water, carbon dioxide, methane, ammonia, all the familiar molecules that make up planetary atmospheres elsewhere, simply cannot form. The atmosphere is a plasma of hydrogen, helium, and metal atoms glowing with thermal radiation. The planet is so hot that heavy metals like iron and titanium are vaporized into the atmosphere. Spectroscopic observations have detected iron and titanium in gaseous form in KELT9b's upper atmosphere. On Earth, iron is a solid metal. On KELT9b, it's a gas floating in the sky. The temperature is high enough that atoms themselves are ionized, stripped of some of their electrons. The atmosphere conducts electricity like a metal. It's more similar to the interior of a star than to any planetary atmosphere we're familiar with. Kelt 9b is also tidally locked, but the temperature difference between day side and night side is extreme. The night side is still incredibly hot, around 1,700 degrees Celsius, but it's cool enough that some atoms might recombine into molecules. This creates a bizarre weather pattern where molecules form on the night side, are carried to the day side by winds, immediately break apart, then carried back to the night side to form again in an endless cycle. The planet is also likely evaporating, though at its large mass, it won't disappear anytime soon. But it's losing atmosphere constantly, creating a tail of gas streaming away from the star. Kelt 9b represents the extreme end of planetary conditions. It's a world at the boundary between planet and star, a place where the distinction between atmosphere and plasma blurs. It's a reminder that planets can exist in conditions far more extreme than anything we ever imagined. The evidence extends beyond our wildest expectations into the realm of cosmic extremes that challenge every definition of what a planet can be. The discovery of hot Jupiters, super-Earths, circumbanary planets, and all the other strange worlds has forced astronomers to completely revise theories of how planets form. The classical model, based on our solar system, suggested that planets form where they're found. Rocky planets form close to the star where it's hot, and gas giants form far away where it's cold. This is called formation in situ, but hot Jupiters can't form where we find them. It's too hot for gas to condense into giant planets so close to stars. So how did they get there? The answer is planetary migration. Planets don't stay where they form. They can move inward or outward through the protoplanetary disk due to gravitational interactions with the disk material or with other planets. Hot Jupiters probably formed farther out, in the cold outer regions of their systems, then migrated inward over millions of years. As they moved through the gas disk, they transferred angular momentum to the disk material, causing them to spiral toward their stars. But this creates another problem. If planets spiral inward, why don't they fall into their stars? Some probably do, but others are saved by various mechanisms. The protoplanetary disk dissipates after a few million years, stopping the migration, or the planet reaches the inner edge of the disk where migration halts, or tidal interactions with the star circularize the orbit and prevent further inward motion. Super-Earths also migrate. Computer simulations show that planets in the super-Earth size range naturally migrate inward rapidly, piling up close to their stars. This explains why most super-Earths are found in tight orbits, much closer than Mercury orbits the Sun. But if migration is common, why doesn't our solar system have hot Jupiters or close-in super-Earths? Why are Jupiter and Saturn still far from the Sun? The answer might involve Jupiter itself. Models suggest that Jupiter did migrate inward early in the solar system's history, moving from about 5 astronomical units to about 1.5 astronomical units. But then Saturn formed and began migrating inward as well. When the two planets reached an orbital resonance where their orbital periods had a simple ratio, their combined gravitational effects on the disk reversed their migration. They moved back outward, returning Jupiter to roughly its current position. This sequence of events is called the Grand Tack hypothesis. It explains why Jupiter is where it is and why the inner solar system has relatively little mass. As Jupiter migrated inward, it scattered material inward toward the Sun and outward toward the outer solar system, depleting the region where super-Earths would have formed. If this hypothesis is correct, then our solar system's architecture is the result of a specific sequence of events that might not happen in most systems. We might be unusual precisely because we don't have hot Jupiters or super-Earths. This forces us to reconsider fundamental assumptions about planetary systems and about how common Earth-like worlds might be. If our solar system is atypical, then Earth-like planets in similar orbits might be rare, or they might be common, but in systems that look very different from ours. For decades, the habitable zone was simple, the range of distances from a star where liquid water can exist on a planet's surface. Too close and water boils away. Too far and water freezes. Earth is in the habitable zone. Venus is too close, Mars is too far, though it was probably in the habitable zone in the past. But exoplanet discoveries have revealed that habitability is far more complicated. First, the habitable zone depends on the type of star. Red dwarfs, the most common type of star in the galaxy, are much cooler than the Sun. Their habitable zones are much closer, sometimes within 0.1 astronomical units. At these distances, planets are likely tidally locked, always showing the same face to the star. Does this make them uninhabitable? Maybe. Or maybe atmospheres can transport heat around the planet, preventing one side from freezing. We don't know. Red dwarfs also produce powerful flares, blasts of radiation and charged particles that can strip away planetary atmospheres. Planets in the habitable zones of red dwarfs are subjected to these flares constantly. Can life survive such conditions? Again, we don't know. Second, liquid water on the surface might not be necessary for life. In our own solar system, Europa and Enceladus, moons of Jupiter and Saturn, have liquid water oceans beneath thick ice shells. These oceans are kept liquid by tidal heating, not by sunlight. They're far outside the traditional habitable zone, yet they might be habitable. If subsurface oceans count as habitable environments, then the habitable zone extends far beyond the narrow ring where surface water is stable. Ice-covered water worlds might exist throughout planetary systems, orbiting far from their stars, yet harboring life beneath their frozen surfaces. Third, atmosphere matters enormously. Venus is similar in size to Earth and receives only twice as much sunlight. It should be hot, but not impossibly so. Instead, it's a hellscape with surface temperatures of 460 degrees Celsius, hot enough to melt lead. The reason is a runaway greenhouse effect. Venus's thick carbon dioxide atmosphere traps heat so efficiently that the planet became uninhabitable. Conversely, planets farther from their stars than the traditional habitable zone might be kept warm by greenhouse gases, extending the habitable zone outward. Early Mars was probably warmer and wetter than it is today, despite being at the outer edge of the Sun's habitable zone, possibly due to a thicker atmosphere with more greenhouse gases. Fourth, life might not require liquid water at all. On Earth, all life uses water as a solvent, but in principle, other liquids could work. Saturn's moon Titan has lakes and rivers of liquid methane, and ethane at temperatures of negative 180 degrees Celsius. Could life use methane instead of water? Could there be biochemistries we've never imagined, functioning in conditions we'd consider completely hostile? These possibilities vastly expand the number of potentially habitable worlds. If we're only looking for Earth analogs, rocky planets orbiting sun-like stars at 1 astronomical unit with liquid water on their surfaces, we might miss most of the life in the universe. The most profound implications emerge when we consider that habitability might not be about planets at all, but about niches. In our solar system, potentially habitable environments include Earth's surface, Europa's subsurface ocean, Enceladus's subsurface ocean, Titan's hydrocarbon lakes, and possibly even Venus's upper atmosphere where temperatures and pressures are more moderate. In a galaxy with hundreds of billions of stars and trillions of planets and moons, the number of potentially habitable niches might be almost incomprehensibly large. Life might be common, just not in the ways we expected. Recent breakthroughs suggest we're entering a golden age of exoplanet characterization. We've moved beyond simply detecting planets to studying their atmospheres, compositions, weather, and potential habitability in detail. The James Webb Space Telescope, launched in 2021, is revolutionizing exoplanet science. Its infrared instruments can analyze the atmospheres of exoplanets with unprecedented precision. In 2023, Webb detected carbon dioxide in the atmosphere of WSP-39b, a Saturn-sized planet 700 light-years away. This was the first unambiguous detection of CO2 in an exoplanet atmosphere. Webb has also detected water vapor, methane, sulfur dioxide, and other molecules in exoplanet atmospheres. More importantly, it can study smaller planets, including super-Earths and mini-Neptunes, worlds that are too small for previous telescopes to characterize in detail. In the coming years, Webb will observe dozens of potentially habitable worlds, looking for biosignatures, molecules that might indicate life. Oxygen in combination with methane could be a biosignature. So could certain hazes or combinations of gases that are difficult to produce abiotically. Webb won't definitively detect light, even if it finds oxygen and methane on a rocky planet in the habitable zone. That wouldn't be proof. These gases can be produced by geological processes, but it would be tantalizing evidence enough to target that planet for more intensive study. Beyond Webb, the European Extremely Large Telescope, currently under construction in Chile, will have a 39-meter mirror, making it the largest optical telescope ever built. It will be capable of directly imaging some nearby exoplanets and studying their atmospheres by analyzing the light reflected from them, not just the light filtered through them during transits. The Nancy Grace Roman Space Telescope, scheduled to launch in 2027, will hunt for exoplanets using gravitational microlensing, a technique that can detect planets that don't transit and aren't close enough to cause measurable stellar wobbles. Roman will find planets in wide orbits, including Jupiter and Saturn analogs, giving us a better sense of which systems look like our solar system. Looking further ahead, the Habitable Worlds Observatory, currently in planning stages, is explicitly designed to image and characterize potentially habitable Earth-sized planets around Sun-like stars. It will be capable of directly imaging dozens of nearby Earth analogs, studying their atmospheres for biosignatures, and potentially discovering life on other worlds. These missions will answer questions that were pure speculation just decades ago. Are we alone? Is Earth unique? How common is life in the universe? As our catalog of exoplanets grows, patterns are emerging that tell us about the nature and frequency of different types of worlds. Current estimates suggest there are more planets in the Milky Way than there are stars. With about 200 billion stars, that means at least 200 billion planets, possibly far more. Roughly 30% of Sun-like stars have at least one planet between 0.5 and 1.5 Earth-radii orbiting closer than Mercury's orbit. These aren't necessarily habitable, but they're rocky and they're everywhere. About 10 to 20% of Sun-like stars have planets in the habitable zone. Extrapolating to the entire galaxy, there could be tens of billions of potentially habitable planets around Sun-like stars alone. If we include red dwarfs, which make up about 75% of all stars, the numbers increase dramatically. Many red dwarfs have rocky planets in their habitable zones. The nearest exoplanet, Proxima Centauri b, is a roughly Earth-mass planet orbiting in the habitable zone of Proxima Centauri, a red dwarf just 4.2 light-years away. Super-Earths are the most common type of planet, found around roughly 50% of all stars. Mini-Neptunes, slightly larger planets with thick hydrogen atmospheres, are also extremely common. Hot Jupiters, despite being the first type of exoplanet discovered and dominating early catalogs, are actually rare. Less than 1% of stars have hot Jupiters. They're easy to detect, which is why they were found first, but they're not common. Jupiter and Saturn analogs, gas giants in wide orbits, are found around about 10% of Sun-like stars. This suggests that solar systems like ours, with giant planets far from the star, are not the majority, but not vanishingly rare either. Planets orbiting binary stars are surprisingly common. At least 10% of binary star systems, possibly more, have planets. This doubles the number of stars that might host planets. Rogue planets, worlds ejected from their stellar systems and drifting alone through interstellar space, might be extremely common. Some models suggest there could be more rogue planets in the galaxy than there are stars. These worlds would be dark, frozen, unobservable except through rare gravitational microlensing events. They represent an entire hidden population of worlds that we're only beginning to acknowledge. These statistics paint a picture of a galaxy teeming with worlds. Planets are not rare, special objects. They're the norm. Most stars have them. The diversity is staggering, the numbers overwhelming, and this is just one galaxy. There are 2 trillion galaxies in the observable universe. If each galaxy contains hundreds of billions of planets, then the total number of planets in the universe is on the order of 10 to the 23rd power. That's 100 billion trillion planets. In that vast ensemble, worlds like Earth with liquid water, stable climates, and complex chemistry are probably common. The number of potentially habitable worlds is so large that it becomes almost meaningless. This forces us to confront the Fermi paradox with renewed urgency. If planets are so common, if potentially habitable worlds number in the billions just in our galaxy, where is everybody? Why haven't we detected any signs of alien civilizations? Maybe intelligence is rare. Maybe technological civilizations destroy themselves. Maybe they're out there but we haven't looked long enough or hard enough. Or maybe life is common but intelligence is a fluke, a random accident that happened once on Earth and nowhere else nearby. We don't know, but the sheer number of planets means that, even if the probability of life arising on any given world is extremely low, the absolute number of inhabited worlds could still be substantial. The universe is full of worlds. The question is whether it's full of life. The exoplanets we've discovered so far are biased towards certain types of worlds. Our detection methods favor large planets in close orbits. They're easier to detect because they cause bigger stellar wobbles and block more starlight during transits. This means there are entire classes of planets we've barely begun to explore. Earth-sized planets in Earth-like orbits around Sun-like stars are at the edge of our detection capabilities. We've found a few, but there are probably billions in the galaxy that we haven't detected yet. Similarly, planets in wide orbits like Jupiter and Saturn are difficult to detect. The radial velocity method works, but requires decades of observations to detect the subtle wobbles caused by distant planets. The transit method doesn't work for distant planets unless we happen to observe them for many years and catch multiple transits. Gravitational microlensing can detect distant planets, but the events are rare and non-repeating. This means there could be common types of planets that we've barely sampled. Maybe most stars have Jupiter analogs in wide orbits, but we haven't observed long enough to detect them. Maybe Pluto-like worlds in the outer regions of planetary systems are ubiquitous, but too small and distant to detect with current technology. There are also exotic planet types that we've theorized but never observed. Ocean worlds covered entirely in liquid water with no land. Carbon planets with surfaces made of graphite and oceans of liquid hydrocarbons. Iron planets, the naked cores of worlds that lost their mantles in giant impacts or evaporation. Helium planets, stripped of their hydrogen atmospheres but retaining heavier gases. Some theorists have proposed even stranger possibilities. Planets with atmospheres of metallic hydrogen at high pressures. Planets orbiting black holes subjected to extreme relativistic effects. Planets with double cores formed when two planetary cores merged in a collision. Planets with rings like Saturn but made of rock or ice or even liquid. And then there are the worlds that might exist in globular clusters, the ancient dense collections of stars in the galactic halo. These stars are metal poor, formed when the universe was young, before supernovae had enriched the interstellar medium with heavy elements. Can planets form in such environments? If so, they'd be made of almost pure hydrogen and helium, utterly unlike anything in our solar system. The possibilities are endless. Every time we develop new detection techniques or new instruments, we find new types of worlds we never expected. There's no reason to think we've seen everything. The universe has had billions of years to experiment with planet formation. We've been looking for exoplanets for 30 years. We've barely scratched the surface. The discovery of thousands of exoplanets raises questions about humanity's future. If there are so many worlds out there, could we ever reach them? Could we live on them? The nearest exoplanet, Proxima Centauri b, is 4.2 light-years away. With current technology, it would take tens of thousands of years to reach it, even with advanced propulsion systems like nuclear pulse drives or antimatter engines. It would take centuries. But assuming we develop the technology for interstellar travel, could humans survive on exoplanets? Almost certainly not on most of them. The vast majority of exoplanets are hostile, hot Jupiters with no solid surface, ice giants with crushing atmospheric pressures, rocky worlds with toxic atmospheres or extreme temperatures. Even potentially habitable worlds would present enormous challenges. Different gravity, different atmospheric composition, different microbes, different biochemistry. A planet might be habitable for native life but lethal for humans. Terraforming, the process of engineering a planet to make it suitable for human life, has been proposed for worlds like Mars. But terraforming an exoplanet light years away would be exponentially more difficult. difficult. It might take thousands or millions of years, and there's no guarantee it would work. More likely, if humans ever live on exoplanets, we'll do so in sealed habitats, artificial environments that recreate Earth's conditions, or we'll engineer ourselves, adapting human biology to survive in alien environments through genetic modification or cybernetic enhancement. Some researchers have speculated about finding planets that are already perfect for human life. Earth 2.0 worlds with oxygen atmospheres, familiar temperatures, and compatible biochemistry. But even if such worlds exist, they might already be inhabited. Would we have the right to colonize them? Would we contaminate them with Earth life, destroying native ecosystems? These questions are currently academic. We don't have interstellar travel. We haven't found any definitively habitable planets nearby. But in the long term, assuming humanity survives and continues to develop technology, these questions will become urgent. The existence of billions of worlds throughout the galaxy expands the potential scope of human civilization almost infinitely, but it also highlights how fragile and precious Earth is. Of all the thousands of planets we've discovered, none is quite like home. Every exoplanet discovery brings us closer to answering the oldest question: are we alone? The search for extraterrestrial life has focused on finding biosignatures, indicators that life is present on a distant world. The most promising biosignature is oxygen in the atmosphere of a rocky planet in the habitable zone. On Earth, oxygen is produced by photosynthetic light. Without life constantly replenishing it, atmospheric oxygen would disappear, reacting with rocks and organic matter. But oxygen alone isn't enough. Oxygen can be produced by non-biological processes. Ultraviolet light from a star can split water molecules, releasing oxygen. This is probably happening on some exoplanets even without life. The strongest biosignature would be oxygen in combination with methane. On Earth, these two gases are produced by life and they react with each other, so they can only coexist in an atmosphere if something is constantly producing both. If we found significant amounts of both oxygen and methane in an exoplanet's atmosphere, it would be strong evidence for life. Other potential biosignatures include certain organic molecules, atmospheric hazes, or combinations of gases that are thermodynamically unlikely without life maintaining them. The James Webb Space Telescope is searching for these biosignatures now. In the coming decade, as more powerful telescopes come online, we'll examine dozens of potentially habitable worlds in detail. But even if we find biosignatures, we won't have proof. We'll have evidence, strong evidence perhaps, but not certainty. The only way to be certain would be to go there, or to receive a radio signal from an intelligent civilization. Which brings us to SETI, the search for extraterrestrial intelligence. For over 60 years, SETI programs have listened for radio signals from alien civilizations. So far, silence. But we've only searched a tiny fraction of the galaxy, and only at certain frequencies. The absence of detected signals doesn't mean aliens don't exist. It means we haven't found them yet, or they're not broadcasting, or they're too far away, or their signals are too weak, or they communicate in ways we haven't thought to look for. The Breakthrough Listen project, funded by tech billionaire Yuri Milner, is conducting the most comprehensive SETI search ever, observing millions of stars across a wide range of frequencies. So far, no confirmed or artificial signals, but the search continues. The discovery of thousands of exoplanets has transformed SETI from a speculative search to a targeted scientific program. We now know where to look. We know there are billions of potentially habitable worlds. We know that the ingredients for life are common throughout the universe. The most profound implications emerge when we consider that we might be on the verge of answering the biggest question humanity has ever asked. Within our lifetimes, we might discover life on another world. We might find evidence of intelligence beyond Earth. We might learn that we're not alone. Or we might confirm that intelligence is rare, that we're isolated in a vast, empty universe full of planets but devoid of minds. Either answer would be profound. Either would change everything about how we see ourselves and our place in the cosmos. We stand at the threshold of discovery. The evidence is accumulating. The technology is improving. The answers are out there, orbiting distant stars, waiting to be found. We began this journey with a simple premise. The universe is full of worlds stranger than anything science fiction imagined. We've traveled from the first exoplanet discoveries around 51 Pegasi and Pulsar B1 to 57 plus 12, through the flood of Kepler discoveries, to detailed characterizations of alien atmospheres by the James Webb Space Telescope. We've explored hot Jupiters where glass rains sideways at supersonic speeds, water worlds with exotic ice beneath global oceans, planets darker than coal and planets being torn apart by their own stars, worlds with two suns and worlds with no sun at all. We've seen how planet formation theory has been completely revised to account for migration, planetary diversity, and the strange architecture of most planetary systems. We've explored how the habitable zone is far more complex than we once thought, and how life might exist in places we never expected to look. The evidence is overwhelming. Planets are everywhere. They outnumber stars. They come in every size, composition, and configuration imaginable, and many we never imagined. The galaxy is full of worlds, billions and billions of them, each unique, each with its own story written in the laws of physics and the accidents of formation. This doesn't mean we understand planets. Every new discovery raises new questions. Why don't we have hot Jupiters or super-Earths in our solar system? How common are Earth-like worlds? Can life exist on tidally locked planets? What happens in the subsurface oceans of ice-covered worlds? What we do know is that our solar system is one data point among billions. The planets we grew up learning about, Mercury through Neptune, represent one possible outcome of planet formation. But they're not typical. They might not even be common. The universe has been running the experiment of planet formation for billions of years, in trillions of different environments. The result is an almost infinite diversity of worlds. Some are hellish, some are frozen, some might be habitable, some might harbor life, some might be home to civilizations looking up at their own skies, discovering exoplanets of their own, wondering if they're alone. The current scientific consensus is that planets are the rule, not the exception. Most stars have them. The diversity is staggering, and somewhere in that vast collection of worlds, there are almost certainly planets where the conditions are right for life. Whether life actually exists on those worlds, we don't yet know, but we're looking. We're searching, and we're getting better at it every year. The next few decades will be transformative. We'll discover thousands more exoplanets. We'll characterize their atmospheres in detail. We might find biosignatures. We might discover life beyond Earth. Or we might learn that while planets are common, life is rare. That Earth is precious not just because it's our home, but because it might be one of the only living worlds in a galaxy full of barren rocks and dead oceans. Either way, the journey of discovery continues. Every new planet we find expands our understanding of what's possible. Every strange world reminds us that the universe is larger, more complex, and more wondrous than we ever imagined. Right now, there are planets orbiting stars you can see with the naked eye. There are worlds out there waiting to be discovered, waiting to challenge our assumptions, waiting to reveal new secrets about how nature works. The universe is full of worlds. Some are familiar, most are strange, all are real, and we've only just begun to explore them. The cosmos is vast. The planets are endless. The discoveries continue.